Welcome to Recording 1A on Infinite Geometric Series for Unit 1, Chapter 1, Mathematics 2200. We'll be developing a formula for the sum of an infinite geometric series, but I have to emphasize, you cannot find the sum for all infinite geometric series, but there are certain ones you can, provided they meet this restriction where the common ratio is between -1 and 1, and of course we can't have a common ratio equal to 0. From Section 1.4, we have this formula for the sum of a finite series. Term 1 outside of r to the n minus 1 all over r minus 1. I present here, right away, the formula for the sum of an infinite series. The sum of an infinite number of terms is equal to T1, term 1, over 1 minus r, where n belongs to the natural numbers, provided, of course, there's the common ratio is between -1 and 1, and the common ratio is not equal to 0. Notice that this little, looks like a sideways 8, is the symbol for infinity. So that's what this symbol here means, is the sum of an infinite number of terms. Now let's compare these two formulas. This one has r to the n minus 1. This one just has the T1, the term 1. This one has r minus 1 down here. This one has 1 minus r. So there's some similarities there, but not quite the same. Something's missing and something's changed around. How are they related? Let's see. You should take out your calculator and do some of these calculations. For example, a half exponent 10 is 1 exponent 10 over 2 exponent 10. That's 1 over 1024. To help you understand your calculator, you probably got something like this displayed, at least in the graphing calculator. That means you got approximately 9.765625 times 10 to the -4. Move that decimal place 4 places to the left. So you get decimal 0.009765625. Now the next one, you get 1 over 2 to the 100. Let's analyze that one a little more closely. That's 1 exponent 100 over 2 exponent 100. So the top stays as 1 really, and the bottom really gets huge. And it works out to approximately 7.9 times 10 to the -31. Pretty small. For this one, I've got 1 to the 1,000 over 2 exponent 1,000. That's too small for my calculator to handle. It even tells me it's 0, but it's not. It's just close to 0. And of course, if that one is, then this one must also get close to 0. So it gets closer and closer to 0 as the n values get larger. In other words, as n tends towards infinity, the values of the expression get smaller and smaller. For the next one, for decimal 99 exponent 10, I get decimal 904, I'll give it approximation here, decimal, approximately that. Decimal 99 exponent 100 is approximately decimal 3660. And decimal 99 exponent 1000 is approximately 4.3171 times 10 to the -5. So it's pretty small. And for the last one, I get 2.2489 approximately times 10 to the -44. So yes, that one's getting small as the n values get large. Let's analyze these first two a little bit more. Here we have a smaller numerator than the denominator, and so that's going to increase more slowly. This one here, that's really the same as 99 over 100. So the numerator and the denominator are closer in value, but the numerator will still increase much more slowly over time than the numerator will. For this next calculation, -.75 is the same as -3/4. 3 is smaller than 4, so the top is going to increase more slowly than the bottom. So a bunch of calculations for those four. These two are actually too small for my calculator. My calculator actually tells me it's 0, but it's not. It's just close to 0. So the expression does get closer and closer to 0 as n gets large. For the last one, 1.1 is the same as 11/10. So we have a larger numerator. Therefore, our numerator will increase faster than our denominator. And indeed, as we substitute in those values for n, the values that we get are increasingly large, and this last one is too large even for my calculator. So this one does not get close to 0. Therefore, in general, r to the n approaches 0 for large values of n approaching infinity. Only if -1 is less than r less than 1. We have a fraction between -1 and 1, and of course we can't have r being 0. Let's apply that idea to a proof of our formula. We start with the finite series formula from our last recording. Since we're talking about an infinite series anyway, we're talking about very large values of n. And if that value of r happens to be between -1 and 1, then r to the n will get very close to 0 for very large values of n. In other words, this part of our formula becomes 0. So we essentially have term 1 outside of 0 minus 1 all over r minus 1. So in these brackets I get -1. Now our formula I presented earlier, this one here, has 1 minus r, not r minus 1. We can take care of that issue by taking out a negative from these two terms, and we've got -r plus 1 in the brackets. So this -1 will cancel out. Well, I'll take out a -1 from the bottom. So they'll cancel out, and we've got term 1 over, reorder these two terms, and I've got 1 minus r. In conclusion, we use the finite series formula considering when r is between -1 and 1 and large values of n in order to prove the infinite series formula.